A composite material or solid can have layers in series, parallel, or combination of both. And let's look at each of them here briefly. When we have this resistance to thermal flow in series, then the overall thermal resistance is going to be the summation of its resistance. So it's going to be sigma R, which is R1, R2, R3, and we call it resistances are additive. Of course, when we have them in series, similar to what you have seen, let's say this is resistance 1, resistance 2, resistance 3, then we have Q. That's when we have it in series. Now, when we have the layers in parallel, so let's say we have the arrangement in a way, so this is in series, but when we have them in parallel, let's say this is R1, R2, 3, R4, and then we have a flow passing through them. The R overall is going to be 1 over R2, the rest go to the sigma R minus 1 all to power minus 1. So here we have currents are additive. So by currents is like this Q is getting portion of that goes to R1, like Q1, portion of that goes here, Q2, Q3, and portion of that goes to the fourth layer or the other layers that are in parallel. So these are the two general configurations. You can easily come up with each of them. We have seen that for the layers in series, but you can easily get the one for the parallel too. So this is parallel. To add here, this is for resistances in parallel. Now, when we have resistances in series, we have so when we have them in series, the overall thermal resistance is more than any single one, or in another one, another word, or overall is greater than, let's say, R1, R2, R3, and that brings us to a concept called controlling resistance. So for this case, let's say if there is a layer with a really high resistance, that's the one that is going to control. So no matter, let's say if you have, I don't know, 3 or 10 or whatever number of layers that are arranged in series here, and let's assume one of them has a very high resistance, in compared to other ones, no matter how low resistance or high conductive the other layers are, this resistance is going to dictate what's going to be the heat flow rate, or it's going to act as a great barrier there. So that's how we define a concept called controlling. So we have a, for this case, we have a controlling resistance. So assuming if, let's say, R1 is much larger than or any of them, then what you're going to see here when you do evaluation of R overall is going to be roughly equal to R1. Now, if we have resistance in parallel, so when we have them in parallel, the overall thermal resistance is less than any individual one. Or in another word, this R overall is less than R1, R3. Now there is another part. We have a concept of R value that we are using in building industry. So if probably you have come across like R values of a material. So note that the concept of R value in building industry, or for, let's say, for insulators or other building materials is based on unit area. Remember, when we are evaluating this thermal resistance, area comes to the equation for R. Now there is a concept of R value that probably you have seen, that like materials, the R value of different materials, especially for insulators, when we are using for the buildings, those R values is exactly thermal resistance, but they are per unit area. So those are this thermal resistance divided by area.